Okay, so today we're going to talk about force. And in physics, a force is any interaction that, when unopposed, will change the motion of an object. Right? So we're actually defining force in terms of the motion of an object. So, for example, if I had this box here, and I, attach it to this rope, and I'm over here, and I pull this rope. Mia's smiling. Okay. And I pull the rope, right? I've put a force on that rope if this object will start to move, right? We measure force in a unit called newtons. Okay. That's our standard unit. We can also measure force in pounds, right? This is the one we're all familiar with, right? We all know how many pounds we weigh. I weigh 210 pounds, and that's the force that I put on the earth when I stand on it, right? Or someone else, if I was to stand on them, that's how much force I would be putting on them, 210 pounds, right? So however much you weigh is how much, force you're putting on the earth. Okay, so back to our example with this box, right? I might, pull this box with a force of, let's say, 5 newtons, right? But let's say my brother over here, who has a identical box, but wants to show me up, and is just a little bit, let's draw some muscles, just a little bit buffer than I am, pulls on this box with his muscles, like there, with a force of 50 newtons, right? What's the difference going to be in my box's motion and my brother's box's motion? Well, it turns out that force is related to acceleration. I'm just going to kind of draw a squiggly arrow. Related to, because I don't want to give away anything. It's related to acceleration. Okay? So that means when I pull this, I'm going to, let's say, have a small acceleration. And when my brother pulls his box, with a bigger force, he's going to have a big acceleration. Okay? Okay, so we're going to keep talking a little bit because I also want to talk about, and let me clear this off, how to represent forces. Okay? And to do this, I'm going to introduce another key term called a free body diagram. Body diagram. Otherwise known as an FBD. So for this, in blue, I'm going to draw a book. Okay, here we go. And I've got my book here. And my book is going to be sitting on this brown little table here. And it's just kind of casually resting there on the table. Now, I might ask, what forces are on this book, right? What forces are on the book? Okay. Well, we know gravity, right? Gravity's pulling the book down. Okay. But there must be other forces, right? Because if it was just gravity pulling this book down, well, the book would start moving down. But we know a book sitting on the table doesn't start moving down. And that's because there's another force from the table pushing up. And this force we call the normal force. Okay? That's just the name we gave it, right? Normal force. So to make our life easy, right? So I don't have to get my artistic skills out and draw a book and a table or whatever I may be trying to represent, a ball and a thrower or really anything here. What we can do instead is represent our forces really conveniently with what's called a free body diagram. And all that is we just use a dot to represent our object. In this case, my dot is representing the book. And then all we have to do is draw the forces as arrows. So the force downwards is gravity. And in this case, I've got normal force going up. Okay, so this is an example of a free body diagram. Let's try another one. So let's imagine instead of a book on a table that we had a ramp, and we had a ball rolling down a ramp. So in this case, let's use green. I've got my ramp. Okay, and I don't know, let's make the ball this color. Okay, and now I want to draw the free body diagram for this ball. Well, I put the dot, and then all I've got to do is think about, well, what are the forces on this ball? Well, right now it's pretty easy. I've got gravity down, and I've got normal force. Well, it's actually a little bit tricky here because in this case, right, this ramp is slanted, so the normal force is slanted. Normal force. Right, gravity always points down. Oops, kind of ran out of room there. Normal force. Gravity always points down, right? Well, in fact, down is defined by gravity, right? The only reason we know which way down is because it's the way in which gravity points. But other forces, like normal force, can change direction. So let's add a little bit of complexity here. And let's say I had a person who, didn't want this ball to fall, and so, was pushing it with all their might, pushing it up. Well, then we would have to add a force. Right, in this case, this person, right, is applying, so we might call it applied force, is applying a force in this direction. Okay? So our free body diagram can have as many forces as are on the object, but only forces that are on the object, right? Notice I didn't talk about, what forces were on the ramp or what forces were on the person. For this particular thing, right, for this particular free body diagram, I stuck to only the forces on the ball. I could also draw a free body diagram. Let's get an eraser out here. Let's get a better eraser. Actually, let's do this. So we can just delete this. Oh no. Well, bear with me here. Okay, there we go. Now we can erase. Okay. So let's say instead of the free body diagram for the ball, I wanted to do a free body diagram for the person. Well, in this case, I'll draw a blue dot because the person's blue. And then I would draw, well, gravity's still acting on this person, right? So gravity. Right, we've still got normal force. The ramp is still slanted, so still got normal force. Let's just call it NF, normal force, abbreviate it. And in this case, right, we don't have anything pushing up on this person, right? But rather we have the ball pushing down. And then we could call this, again, the ball is applying a force, so we might call it the applied force. Okay? But notice how this free body diagram, the one of the person, looked different than the one with the ball.